Okay.
Got it. And
Okay, well, thank you for the introduction. I'm honored with your great introduction to myself. So today we're going to talk about Web3 security. Obviously, we won't be able to cover every single aspect of blockchain and blockchain security just because there's so many events happening literally every day. And yeah, so we're going to be covering mostly the general stuff and some of the common mistakes that developers and project builders make, as well as some of the cryptocurrency exchanges and mainnet, all the participants of this Web3 ecosystem. Yeah, sorry. So Jason actually gave us like a really good overview of who we are, but just to introduce ourselves again, we've won a lot of capture the flag, like it's hacking competitions that we do. We've won a lot of them, including some of the Web3 specific CTFs that are run by Paradigm and Newman Soft. And we also have reported a lot of vulnerabilities in global vendors for Google, Microsoft, yeah, those companies, as well as we also reported some of the bugs in Ethereum. We actually, Juno here, I can kind of say him.
hello.
Juno actually found and reported a bug in Ethereum like chain that can just bring down the entire Ethereum. This was back in like 2017 where, Vitalik just started doing the Ethereum. So we didn't get much attention / bounty. I assume if we reported that bug right now, we would have gotten millions of dollars, but it was like what, $20,000 back then. So, but still, like we've been actually finding these serious and critical bugs and reporting them to the vendors and project builders to make the Web3 ecosystem safer environment. So today we're going to talk about a lot of things, but we're going to start with cybersecurity. So I know a lot of you are technical background, some of them are not, but probably most of you haven't really got a chance to kind of learn or even think about what cybersecurity entails. Okay, everyone talks about, oh, security is important, but like, what does it mean to do cybersecurity? So we're gonna kind of briefly walk on that, and then we're gonna move to blockchain cross security. So like, what does it mean to do cybersecurity in blockchain field, right? And then we're going to look at some of the examples and security threats in Web3 specific domain. And then since a lot of these projects are Ethereum forked and Ethereum based, so a lot of them use Solidity as their programming language. And Solidity is great, but also it has very many pitfalls that people can fall through and make mistakes that will result in millions of dollars lost. So we're going to look into common mistakes that people make in Solidity and how the Solidity, the language itself, has gotten improved over the past few years. And then we're going to look at some of the real world examples. So we'll be looking at some of the study cases actually for real incidents where millions of dollars have been lost. We may have time or not have time, but we may be able to talk about recent events that involves hacking. And then finally, we're gonna close on the note, basically showing, in order to future-proof our security in Web3, like what can we do as a community, as individuals, as developers, as project builders. So yeah, we're going to start with security in cyberspace. So here we need to define what cyberspace is, right, in order to talk about cybersecurity, because it's we're talking about like physical security. We lock our doors. We have guards that are, protecting our celebrities, president, right? So what does it mean to guard something in cyberspace? So cyberspace is basically a virtual environment with computer systems, right? It can be servers, IDC, cloud. It can mean a lot of things these days, and it's globally connected. And it doesn't only involve these large, beefy servers. Sometimes now we have mobile phones that we use every day, and it's probably more powerful than computers back in 90s or 2000, right? And then smart watches. We have watches, and they're pretty smart, and they're basic computers on your wrist. Cars are getting smarter too. And basically these days, the cars, not even just the electronic cars, but even for the gasoline cars, those are basically like computer machine on wheels, right? These are very electronic centric, heavy cars that have computer systems with ECUs that talk to each other to determine, when to accelerate, how much they accelerate, when to pressure on the brakes, that sort of stuff. And then we use laptops, computers and IoTs, all kinds of computer systems in the world, and they're all connected. And with all these devices connected with the network, that basically makes a real cyberspace. And because of how recent changes like technological evolutions happened, everything is globally connected these days, right? You can basically send messages over the internet, and people on the other side of the globe basically be able to read that message in milliseconds. So you don't actually have to physically move to places to deliver your messages or payments and everything like that. Everything is connected. And especially with COVID, a lot of critical systems and technical systems have been rapidly digital transformized, right? Everyone is moving towards digital transformation, and the acceleration has become really fast, and the dependency to the digital systems have gone up significantly over the past couple of years. And we can think about remote work, contactless, technologies, a lot of metaverse we talked about, all these cyberspaces. A lot of things happen in cyberspace more so than in physical spaces these days. So it's basically breaking down the whole boundaries between what's physical and what's cyber, and it's actually affecting our real life these days. So yeah, let's look at the evolution of cyberspace a little bit. I know it sounds like a history class, but it's important to really understand where all these technology came from and how things evolved in order to actually learn what kind of mistakes have been made and how we have been mitigating them. So cyberspace, the term itself, has first appeared in cyberpunk fiction, authored by William Gibson back in 1982. So it's a pretty old term. And ever since then, in the 90s, I think everyone knows that the internet was, sorry, what was that?
There's a chat.
Oh, the chat. Okay, sorry. Oh, that was, sorry. There was a chat, so we had to check. Sorry. But the internet itself was actually developed by United States government, DoD, for military purposes back in 60s. And then later, it kind of expanded into commercial land with the enterprise markets and stuff. So with the internet, a lot of things were connected. It kind of expanded exponentially, and we were able to do a lot more things faster and easier and cheaper. And then there comes .com era. So some of you may not have experienced this era at all, but it's in late 90s and early 2000, massive growth in internet adoption and technology, right? So Netscape, Yahoo, eBay, Amazon, all these and Google, all these companies have come up and were very, emerged. And you can kind of see in the graph, that's the famous .com bubble where it pops, and then you can kind of see a steep decline in, a lot of money is going away and a lot of values are going away. So we have some crisis there, but then over time we have recovered, and ever since then we became stronger, and a lot of technology has been more, people started concentrating on fundamentals, right? And people invested in more in tech. And in 2023, the year that we're living in, the current stage, you can see a lot of cloud infrastructures are very common. Everyone gets their own, Docker or Kubernetes instances, microservice architecture, things that we haven't really thought about, 10 years ago. A lot of technologies are emerging. And obviously, related to our course here, blockchain or Web3 has been very popularized. A lot of people. As Jason mentioned with the project notice, it is really important to think about, like, in this perspective of, we have this technology called blockchain, and it's really fascinating and interesting. We're going to talk about it a little bit later, but like, how are we actually using it? Like, is it really necessary to use this technology for the problem that we're trying to solve, right? So we're in this weird era where everyone's trying to solve everything with blockchain, but I don't think that's the best way. But hopefully, with that effort, we're gonna see a lot more, killer features coming out, killer apps coming out. The actual exact problems that we can solve only through blockchain. And obviously, the number of internet users are growing fast. We have, you can just kind of see the graph, right? And then current state of the cyberspace, from cloud computing, blockchain and cryptocurrencies, autonomous driving, IoT, robots. We've seen a lot of those too. IoT devices and VR, like here, like, virtual reality, augmented reality, metaverse, a lot of things we have, like, basically cyberspace has come into our real life over the past few years. But what it means is that rise of cybersecurity threats also, has gotten greater, because with every digital technology, there's a cybersecurity threats. And so it became a huge challenge for everyone, because we don't have one solution for everything. Everything just has to be customized, and there are not that many, white hat hackers to protect everyone. So that's an issue. And what makes it more difficult is that in industry, we're not going to even look at the, academia or anywhere else. If you just look at the industry, there are a lot of threats, and as you can see, a lot of these sectors and different industries have very different set of challenges. And as I just mentioned, there is no one solution that just solves everything. For instance, like IT and tech, right? We use a lot of web applications, mobile applications. We use cloud infrastructures, CI/CD, DevOps. So there's now a thing called DevSecOps that, basically protects the DevOps. And in finance, there's also web and mobile applications coming out more recently. There's also financial information that are more, really, the privacy is really important, and there are a lot of security solutions. I assume if you're living in Korea, you've probably heard that some of these, financial security solutions had some incidents. So like North Korea attacked those vulnerabilities to hack into Korean citizens using these, abusing these security solutions. So it's not just about, implementing these solutions, but implementing them securely, right? Solutions that you put in could be abused against you. So designing these solutions is really important. In games industry, cheats and anti-cheats, IP theft, these are really all important. Automotive, as I mentioned, these cars are now becoming a huge computer on wheels. So embedded hardware, firmware, and physical security, all those are challenges in automotive land. And obviously, and most importantly for our purposes, there's Web3. Web3, obviously, it's kind of encompasses all the different industry. Like it has IT and tech, it has finance, it has some game industry for NFT and NFT gamings and stuff, and play to earn, right? And some of them are integrating Web3 technologies into IoT, so it sometimes involves embedded hardware and security stuff. But most notably, there's centralized exchanges like Upbit, Coin1, Bithumb, right? These centralized exchanges are there, and you probably heard as well, GDAC the other day got hacked for, how much was it? Like $18 million, $50 million.
About
Yeah.
18%.
So these things do happen day to day. And there's also decentralized finance, which is DeFi, and there's NFT, SBTs, blockchain, smart contract. There's so many different angles and targets that we have to secure and are exposed to threats. And just to mention, these vulnerabilities aren't just targeted by some crime organizations and crime groups, right? North Korea, it's a state-sponsored attacks. So it's not just like some random people trying to hack and get some money out of it. It's actually nation-sponsored, right? The country itself sponsors these attacks, spend a lot of money and time and effort to actually grab these cryptocurrencies or attack into the government, that sort of stuff. All right. So we kind of looked at, very briefly looked at cybersecurity and what kind of threats there are in industry. We're going to move on to a blockchain specific security issues. So when you think about blockchain, right, people always question, like, I thought blockchain was secure and I thought it was transparent, it's immutable, no one can hack things, right? There's no like 100% secure platform. Mostly because blockchain or any other technology and techniques, human builds them and human is not, perfect, right? So blockchain obviously and does provide some strong guarantees that we haven't had before. For instance, immutability, distributed and decentralization, transparency, and security through cryptographical guarantees and whatnot. But obviously, that doesn't really protect from every aspect of these threats. So we're going to look into some of them. That's mostly because with the new paradigm and new technology, there's always new framework, new code, new code base. So these things appear. So for instance, we have Solidity, we have Cosmosm, we have different type of chains. A lot of them are EVM based, but then there are some completely different chains that are implemented completely separately with different goals, different security aspects and guarantees. There's different languages that are used, right? And there are different layers like L1, L2s, L3s. I don't know. There are L4s now. And then we also use like a lot of new concepts too, which is like ZKP. Like, sure, the zero knowledge proofs and that concept has existed for a really long time, but it's been only recently that we have been using that in production and like real life examples, right? We only talked about this textbook examples before, but now we're actually using it for its purpose. But have you actually spent enough time and effort to validate and verify their security aspects, like their properties? I don't think so, right? Like there are a handful of people who actually understands this mathematics behind ZKP, but everyone's talking about ZKP as if they're experts, right? So with this whole new things coming out so fast, it's very fascinating, and there's a lot of, it's kind of overwhelming almost, right? Sometimes there's too much stuff to learn, but it also means that there's so many attack surfaces and attack, potentials that are coming out along with them. I guess that's basically sums up what I just said. So we're just skip this one. For here, other attack surfaces that we can talk about and threat models that we can talk about are, we now have to think about not just the web app portion, but our backend basically become the blockchain, right? So running the chain and making sure these nodes security and their integrity has been kept securely, the stability of the network, smart contract security, and not to forget the financial engineering attacks that are just not really a part of the attack models before, but with the DeFi, every little code and every little variables that you misuse, it could cost you millions of dollars, right? So those attacks, we have to come up with mitigations, secure designs, access controls, management, everything like that. And smart contract itself had a lot of issues with the language itself, compiler, and how people use them. Yeah, but a lot of them have gotten better and improved over time, but we still see some of the issues that we thought we solved, which is price oracle or reentrance issues we're going to talk about later. These basically very simple concept, but very effective attacks still happen day to day. And then we're going to talk about this one and two later, but you can't ignore all the Web2 front end. Like, so we say, oh, we're now Web3, or different generation of web, we have different technology, but all these websites and applications for usability purposes are hosted on Web2 infrastructure, right? So you can't just ignore them. If your front end server is compromised, then your JavaScript file could be modified, and it could serve malicious code. That sort of stuff didn't go away. And here again, for instance, if you're talking about web app that you have server-side code for, and then you have some front end, sure, you can make some simple mistakes that will result in some service instability. But in here, it's one tiny mistake in smart contract, literally one variable misuse or one line of code could cost you a fortune, right? So doing bug bounties and security audits are very common in Web3. In Web2, it's been really hard for us. We do a lot of, like as Jason mentioned before, we do a lot of industry, like from embedded to Web3, Web2, finance, right? But other than Web3, it's been really struggle for us to convince them why they have to spend money and why they have to invest enough to secure their stuff. But in Web3, people understand that they the risk, and they're willing to pay for it because they know how much damage that can be done if they miss them. And this may not apply in the future as much as it did before. In year of 2011 or 2022, we've seen a lot of kind of no-brainer investment, and there's too much money and too much fund out there. People didn't really think about too deeply like how secure it is, like what if I get hacked here and lose some money, I'm just gonna make it another bash here. So people didn't really care too much. So that kind of resulted in some of the project teams don't really have much fund for themselves, so it's not well funded, but then they have a huge like TVLs, like total value locked. So in their DeFi app, they will have, $300 million locked in, but then the team itself doesn't have that much money to actually afford in-depth, audits or security consulting to pay for them, right? So they're just they do have $300 million worth of assets from their users, but then the security hasn't really been audited. So there's so many cases of that. But with the whole crypto winter coming in, and then hopefully when the spring comes again, people will be more cautious and more take precautions. And actually, the team that actually care about security and invest enough are going to be left with the business, I think. All right. So we kind of looked through whole, what it means to do security in blockchain and its technology. So we're going to look into some of the security threats in Web3. So in Web3, we can kind of break down into 4 different categories of security threats. The first one being the smart contract issues, second one being the blockchain network issues, and the third one being infrastructure and off-chain issues, and lastly, decentralization risks. So we're going to look into each one of them and then just give you examples of what they are. So the first thing is about the smart contract. You can think of it as, the brain of blockchain, right? With the whole Bitcoin and something, like that, we couldn't really have a Turing complete, computation on these networks. But with the Ethereum's popularity and L2s, we're now able to compute these things on-chain, decentralized, distributed, right? So which is fascinating, but then these smart contracts are basically code, and they're basically applications that people write that just runs on a super, distributed computer. So it still has all the issues that we've seen in the past in normal programming languages and normal programs in general, right? So there's reentrance issues, which we had numerously before with the operating systems, with threads and mutex, basically critical sections. How do you guard those resources so that way there's no race conditions and stuff, right? So reentrance is an issue again, and insufficient ACL. Some of the functions should be only called by the owners or people who have the right to do it. But then if it's misconfigured, then anyone can do it. So we can see things like public burn functions. So anyone can just burn tokens. Or public mint functions. Everyone can mint things. You'll be surprised, like you'll be laughing like, oh, like who makes those silly mistakes? You'll be surprised how many people in production actually make that mistake. Integer overflow, underflows, they happen a lot. Thankfully, I'll talk about it later, but thankfully the compiler now helps you kind of automatically, don't even have to think about it, right? Compiler helps you just mitigate those issues. And then, as I mentioned before, financial engineering attacks, those are kind of new in the field in Web3 because of DeFi and stuff. So the code itself may be completely fine, but then it depends on it relies on price oracle from somewhere else, or it has some interest model, like it's mathematical models for interest payments and rewards systems. There could be some financial engineering attacks that people devise, and it has happened before. And also insecure governance model. So like we have all these DAOs and governance systems, but if that's not secure, then people could just kind of rig the votings or pass these proposals without actually going through the proper governance model. And obviously, since it's a program, people can make a lot of logic bugs that are just not intentional, and that can lead to huge damage. The next category that we're going to talk about is the blockchain network. So basically, it's a P2P network, right? That's not something new. Like I assume all of you have experience with these P2P file sharing systems. Like blockchain is not that much different from it, right? Fundamentally. So you have to run nodes, and you kind of have the network of like pool of people and participants that are not trustworthy, and you have to somehow get the consensus out of it, right? So there could be denial of service. So as I just mentioned in the earlier, where we find some vulnerabilities in these implementation of nodes that where we can just take down or crash those nodes altogether, that the network itself just doesn't exist anymore, right? So those issues exist. Pre-compile smart contracts. So for the efficiency and security of it, their networks basically implement some of the pre-compiled code. And if that has bug, then literally everything in the network gets affected by it, right? Remote code execution. We actually found a serious vulnerability where, since what it means to run this node is running some code on your machine, right? That has wallets and everything, other system. Oh, sorry. My Siri is reacting to my voice. But yeah, so what that means is that if attacker finds a malicious input or code that can run on your system and actually get more privilege than they are allowed to, then they can basically compromise your machine. And there have been a lot of mainnet implementations that allow this attack. So we were able to basically send a transaction or deploy a smart contract. And when these things get propagated, all the nodes will be able to connect and actually get root access on them, which is really serious, right? So those are the attacks that are exposed. P2P Eclipse attacks, just because it's a peer-to-peer network. There are certain types of network attacks that are known, which apply to blockchain network as well. Obviously, consensus issues. So how do we make sure who to follow? Like, what's the ground truth? That sort of stuff is very very challenging problem to solve, right? And so that's why we have so many different ways of, proofs, right? Proof of work, proof of, stake, different kind of designs have different, strengths and weakness. And each chain kind of adopts to whatever they think is necessary to secure their consensus securely, as well as, somewhat usable. Like if it takes, hours to confirm and finalize, then it's kind of not really usable. But if you just do it too fast, then there could be a lot of chain splits and there could be double spending and all kinds of, nightmares that happen. Also with the whole, it used to be minor extractable value, MEV, but these days, it doesn't need to be minor, so people call it maximum extractable value. These ones are, in one sense, you're trying to make the this, finance more efficient, but they're also kind of grabbing these opportunities from the users. So like, how do we prevent people from abusing these traits and properties of network inefficiencies for them to gain these profits, right? That's rightfully for the community and rightfully for the users. So these all kinds of network related issues are also security threats in Web3. The next thing we're going to look at is infrastructure and off-chain. As I mentioned before, a lot of backend is now replaced by, say, blockchain itself, and smart contracts. But the front end still, for usability purposes, is still implemented in Web2 technologies, right? You still have servers, you still have web apps, and then off-chain. In order to actually run these nodes and maintain and manage these wallets, you basically have to do key management. It's still rely on this public private key crypto, so you need keys that need to be secured. Well, how do we do that, right? And as I mentioned before, some of these web apps or servers have APIs that doesn't do input validation correctly, so it leads to another security vulnerabilities. Sometimes for bridges, right? Bridge by definition is connecting and bridging different chains. So obviously, two chains may not have a agreed protocol that can talk to each other directly. So what bridges do is that they basically talk to each of the protocol and chains and kind of try to translate messages to each other, right? In order to do that, some of the bridges use the events or logs that can be included in the blockchain, and they parse them. But if they parse it incorrectly or there's a bug in parsing them, then attacker can abuse it to say, basically get free profit or send wrong information to the different chains and contaminate all these information. Obviously, phishing. If you just ask any security people, like all these technologies and financial engineering attacks and all kind of shiny and cool, attacks are really interesting in technical way, but the most damage, like just pure damage, like financial damage, mostly come from phishing. So like normal users, going to this phishing website and put down their seed phrase, put down their, sign their messages and whatnot, and just lose money. So these things are happening. And as I mentioned, North Korea or China are doing state-sponsored cyber attacks, not just only, attacking these smart contracts themselves, but the companies who are building this, right? Who has the keys? We're going to talk about real world examples later, and these things do happen. Lastly, we're going to talk about the centralization risks. So I guess it could, so depending on who you ask, this is a risk, and sometimes it's not, it's a risk mitigation, depending on how you look at it. But when we talk about blockchain, we're under the spirit of, we are for the decentralization, and we're trying to distribute everything, decentralize everything. So anything that, kind of makes some stuff central is a risk for blockchain. So because that creates a dependency, that creates a single point of failure, right? So we're trying to distribute those risks as well. which includes backdoors, rug pulls. Like how many rug pulls did we see over the past 2 years, right? People just kind of copy code and then open their tokens, do the token sale, and then just kind of disappear, right? Scams, and sometimes if it's the POS and everything like that, or POA, majority attacks happen. So people kind of come up, like group up, and they decide, they just rule, what the governance is and what the rules are, which basically breaks, like, why do we even have blockchain at that point? And upgradability, right? We talk about blockchain's immutability and how, like, praise how good it is, but then literally most of the projects just launch proxy contract and then just point it to the different smart contract that they upgraded all the time. And like then immutability kind of breaks there, because sure, your proxy contract doesn't change, but then the implementation could change anytime, which poses some of the centralization risks. Like you could deploy very benign and normal smart contract one day, but then next day you decide to just deploy the code that steals all the money, right? So like how do we maintain and manage those risks in blockchain? And some of them aren't even open source. Some of them are open source, but even with the open source projects, right, it is only meaningful if, in security perspective, if someone actually goes and validate them and verifies that they're safe. But even if it's open source, that doesn't mean that it's secure. That doesn't mean that it doesn't contain backdoors, right? You could put backdoors and just open source it. If no one's going to look at it, then it kind of defeats the purpose. So there are a lot of risks in Web3 realm. All right. Now we're going to talk about smart contract security. Obviously, when we say smart contracts, people think of it as like, oh man, it's a smart contract, so it must be smart. But that doesn't mean that it's secure, right? So whoever named that kind of gives false, hope of, oh, smart contract can do everything and it's, almighty, but it's not. So smart contract is a digital contract executed via computerized transactions. It's basically like, kind of neat way of saying code that's running, I don't know, on a computer. It's a program. So in 1994, Nick Szabo basically proposed this concept, but as you can see, we haven't really used this concept very much until very recently. So it's been kind of buried down for like 30 years. It basically plays the brain role and enables this application development. So we have these traits on blockchain, but it's not like, it's no use if we can't really do anything interesting. And smart contracts is what enables the interesting part to happen. And most blockchains, for that reason, now support smart contracts. So Ethereum being the biggest one, Aptos, Solana, all these blockchains have a way for you to deploy program that can be run decentralized. And smart contracts basically have these traits and properties. And these properties are also, suggested by Szabo, who coined the term smart contracts. One of them is observability. So you can basically, since it's a contract between, say, two people or two organizations or two accounts in blockchain, you should be able to observe what's going on and what's going to happen in what code, right? And what kind of conditions there are. So it's a basically contract, and being able to have the visibility of the content. And then there's a verifiability. So you should be able to basically prove the fact that someone actually, executed this contract or not has executed contract, or someone lied about it. Like they say they're going to do it and then they don't do it, right? That should be possible to basically point at it and say, hey, I did my part, but then the other party didn't do their part, right? Or better yet, with the enforceability, you can basically enforce certain properties, right? So for instance, if I send this much money or this much token, then you give me that token, like the other token back. So those are basically defined in the code and contract itself. So I don't have to call out, like, you know, for sure that that's going to happen. So, and privacy, obviously, obviously only the people who are doing contracts need to know, right? No one else needs to know. But obviously with the blockchain, that's a little bit hard to achieve because by design and nature, it's very transparent. All the transactions that happen on blockchain are public. So in private network, that may be possible, but in normal blockchain and public chains, you can't really have privacy. So that's why there are some L1s or L2s or some, DApps that utilize ZKP to keep the privacy safe while being able to do other, interesting parts. And obviously, because of it, with same thing as internet or Tor, it has the same issue. It's like double-sided blade where, yes, it can protect you from your privacy being exposed, but also it can be abused by, malicious users to launder money or, do some sketchy stuff. So, yeah.
Brian, can
yeah.
I ask something?
Yeah.
Okay. Actually, smart contract is very transparent and anyone can see the code of a smart contract. So we can verify how smart contract works. But on the other hand, any hackers and any attackers can see the code. So they can see, they can find out vulnerabilities of smart contract. So do you think the openness of smart contract increase hackability or incidents?
I definitely think it makes it easier for, malicious hackers to look at the code and find the vulnerabilities. But so in traditional security, there's this saying where, like, security through obscurity. So you're trying to hide information as much as you can to kind of keep you safe. But that only goes so far, right? If you are building something that's secure by design or, get audited and make sure your code is secure, then open sourcing it and everyone's having an access to it shouldn't really affect your security, is my viewpoint. But obviously not everyone is audited and not everyone is, a secure coder. So yes, it does expose the visibility and I guess also increase therefore the hackability of exploitability of these smart contracts if they're open. But we shouldn't really rely on the fact that, oh, attackers wouldn't know this code, right? For instance, even if it's not verified code where you put the source code online or, to the blockchain, the attacker still could look at the bytecode and decompile them, right? So in order to actually do this, then we shouldn't share any code at all, which kind of breaks the whole distributed and decentralization model. So there could be some, ZK applications here. You run the code, but then you don't see. Yeah, that's really difficult. Yeah. So yeah, so I think the way we should approach this problem and challenge is by making sure your code is secure before it gets deployed. I think that's the best bet and best way that we can approach this, and not relying on the fact that attacker not seeing your code. Did that answer your question? Kind of? Okay. Yeah. So I know there have been other lectures before that talk about EVM and their internals. So we're not going to go into too much depth in EVM stuff today, but you can kind of think of EVM as world's computer, right? It's programmable, decentralized state machine. So it's Turing complete, these smart contracts run. EVM architecture, you can think of it as stack-based VM. It's a virtual machine implementation, basically. And you use gas as fee. The reason, there's a gas fee is because resources are not free, right? So all the computers that are running these code and verifying them, need to get incentivized somehow to participate in this network. And so this is more of an incentive mechanism to do that. And then making sure people don't overwhelm the network. So gas price changes depending on how busy the network is. If there's just too much workload and everyone's trying to use the network, then gas fee goes up. So it kind of disincentivizes people from using it. And then if not, too many people are using it, then gas price is cheap. So it incentivizes people to use it again. So it's a mechanism, economic mechanism to ensure network stability. So later we'll talk about it when we talk about solidity security issues. But this gas is really interesting trait, and we have to actually think about it as a developer when you design your systems, because in the past, when we're building like web apps or programs that run on your computer, you don't really think about resources, right? Like, yeah, like use some more CPUs, use GPUs as much as you can, that sort of stuff. But here, every program has very limited resource, and you have to kind of optimize for it. Otherwise, it can be abused for the attack. We'll see an example of that. Yeah, so the apps, use a lot of different languages based on your, blockchain, but we're only gonna focus on Solidity today. It's kind of similar syntax. It's not like a one syntax. It's like some of them are coming from JavaScript, some of them are coming from Java, some of them are from Go. So it's kind of like mixture of. It's a monster. That's why the language itself is kind of shitty, to be honest. But it does provide some basic programming structure as like, arithmetic operations, types, constants, variables, all the things that you expect some, decent programming languages would have. Like you have functions, you have memory, data structures, those sort of stuff. And there are some reserved keywords and global variables that will expose some of the blockchain information to you on chain. And then just like the other, programming stuff, the Solidity language itself basically gets compiled with the Sol-C compiler into bytecode. And then the EVMs basically run bytecode. Yeah. So yeah, so today we'll be focusing on Solidity, but within the Solidity security and smart contract security, there are also like hundreds of other issues that can arise. We're not going to cover all of them because of the time constraint, but we're going to just kind of focus on somewhat easy concept, but detrimental if you make mistakes. And you can kind of search for SWC registry, and you can see all kinds of different scenarios, different types of bugs, vulnerabilities that could happen in a smart contract. So we're going to look at some of them. So the most intuitive and easy to make mistake is integer overflow and underflow, right? This has always become an issue for programmers back in from like C, C++, right? This happens because in computer systems, right, there's only limited resource for registers or computer memory. So in order to basically represent a number or some value, you have to store it somewhere, and that storage is not unlimited. Unlimited, right? So you have to cut off somewhere, and if you basically go over that limit or goes under that limit, the integer overflow and underflow happens. So this is like more of an intuitive example where you have odometer in your car. Hey, you basically have certain number of digits that you can represent, and that goes over, then it becomes 0. So does that mean that my car suddenly became a new car? No, right? Like it just couldn't represent that number in the system, and that's what happens in integer overflow happens. So like this situation we just call wrapping around, but in most like C and C++ languages, they don't really define what happens if integer overflow happens. It's undefined behavior, but compiler usually decides to implement the wraparound. So if you're at the maximum value and then you add 1, it becomes 0, and vice versa. So if you're 0, but then you just subtract 1, then it becomes the maximum value, that sort of stuff. So depending on the type, it has different storage size. So character only stores 1 byte, and that has a value range of how much we can represent, right? But it also depends on, if it's signed versus unsigned. Like obviously signed, you can represent some negative numbers to positive numbers, whereas unsigned, since it's unsigned, you can only represent, 0 and above, and there's no negative numbers here. And depending on that, and because even if it's like unsigned versus signed, you only get that storage size. So for instance, if you look at the unsigned character, it's 1 byte. So if you are only doing unsigned, you can represent from 0 to 255, which is 256 values that you can store in 1 byte, which is 8-bit. In signed character, you can see that you can no longer represent, 200, for instance, because you now have to split that same amount of space to represent negative numbers. So you're now back to like negative 128 to 127. So you can still represent 256 values, but you have to split now. So you can kind of see all these, different types of integers representing different values. So in Solidity, there's like default type of integer is uint 256. So as the name kind of suggests, it's a 256-bit number. And its minimum value that it can have, since it's unsigned, is 0. And so for this example, if the user, puts more than what they have in the amount parameter, then the result of this arithmetic operation is going to be a very large number, right? So it's going to look at the balance, and then it's going to subtract and store that value, the result, to the balance. But if an amount is greater, then it's going to underflow, and then it's going to become very large number, because it can't be uint 256 can't represent negative numbers, right? And this check always passes, right? So this is a common mistake. It looks fine, but then it's actually a very serious vulnerability. And in order to actually check this vulnerabilities and stuff, people implemented their own like safe math libraries, or do these integer checks every time they do arithmetic operations. So it was very hectic since the compiler didn't really support it natively. So whenever you add or subtract or multiply or divide numbers, you have to consider what happens and what's the effect of it, right? And just make sure the underflow or overflow doesn't happen in your calculation. Thankfully, from Solidity 0.8, which was released back in 2020, December of 2020, so it's kind of 2021. But as you know, Solidity and the whole Ethereum was released back in 2016, 2017. So it took them like 4 years to implement the safeguards in compiler, in Solidity compiler. So that's kind of surprising, given how advanced we are in technology, but how not advanced we are in these technology as well. So another issue that could happen, and that happened a lot, and like this shouldn't really happen anymore, but for some reason, somehow people continue to make these mistakes and continue to get funds stolen with the same mistake. So there's a reentrancy bug. So any like interaction from contract A with contract B, right? And say we do transfer or of the Ether or native tokens, basically hands over the control, like program control, to the contract B. This is kind of like how EVM is structured. So that's how it's going to run. But what it makes it possible is that contract B now then, since it gets the control, it can call back into A again before the initial interaction is completed. So you can think of it as more of a recursion. You can kind of recurse through different functions and then come back to it and then call it again, that sort of stuff. So to kind of give you a visible, example, we can look at the examples here. So this function is a withdrawal all function, right? It gets the address to, and anyone can call this. And you can kind of see the logic here where it checks if the balance of the sender is greater than 0. So make sure they have enough balance. And then if so, then they're going to send the amount, that balance that they have, to the address that they specified in parameter, right? And then they're going to make sure once they sent everything, the sender's balance set to 0. So it looks very benign and correct. But what happens is that in Solidity, you can imagine there's an attacker that deploy their contract and do this, right? So they call this function with the to set to basically itself. So they're going to check the balance and it's going to pass. And if you set the to parameter to the contract address, then it's going to call into the contract again that you just got invoked from. So what happens here is that in contract, malicious contract basically calls withdrawal again. So then what happens? It basically, and then you specify the to address something else, then this passes again, and the payable to call happens. So it basically sends the balance twice, right? Because we haven't really finished this logic yet because we got hijacked from this level to the contract again, right? Instead of going to the next line, which sets the balance to 0. So we re-entered this function before it got finished. So what happens is that it calls on the call stack, it basically calls and then sends the money, sends the token, and then it comes back and sends the token again and again. Like you can basically do this n times as much as you can until the the actual balance is over. So you're basically copying money, and then it's going to set the balance to 0. But at that point, it's too late, right? So you can kind of see how reentrancy become an issue because how smart contract and Ethereum works. Similar issues happen in operating systems with threads and critical sections, critical resource and stuff. So that's why you sometimes put mutex. So here, the issue is that check effect and interaction pattern, right? So you basically have to see if check happens, right? So we check if the balance is greater than 0. So that check passes. But then once that you do the check, what happens is that you have to do effect. But you do interaction first here. That's the bug. So you interact before you apply the effects. So that interaction could lead into reentrancy, and then it takes an effect. So in order to actually make this more secure, you have to swap these orderings. So you do check and then set the effects and then do the interaction based on that. But obviously, if you just do line swap, it's not going to work because balance of message the sender is going to set to 0 first, and then you're going to set that send that value to address. So you're going to send 0. So that doesn't make sense. So in this case, you actually have to save the balance in variable and then set the effect, which sets the balance to 0, and then use the stored variable that contains the actual balance before the effect has been set to send to the to address. So, or you can set a lock here. So that way, so there's a modifier called like non-entrant, re-entrant, right? In which case it makes sure that it doesn't allow the re-entrancy. So it's going to set a lock, and then if you already entered this function before, even if the original caller calls back into this function, it's going to revert. So that way you can kind of block the whole re-entrancy. So there are a couple of different ways of remediating this issue. So there are very well-known practices and there are very well-known modifiers that you can use. So this shouldn't happen anymore, but people still kind of forget to do these things and happen to lose a lot of money. Another example that we're going to look at is a denial of service with block gas limit. So I kind of mentioned before, alluded that we have to actually care about the gas limit here, right? So because user pays the gas as a fee, and block basically has some limitation of maximum gas, which is called gas limit. So if you look at this code, like it's gonna be totally fine in say JavaScript or web frontend or your C program, right? And it's gonna be very fast. You're basically going through all the user, like you're updating user information by their name. So you're finding a user in the array that has username and updating with that, age, right? So it's very benign looking, but then if you have more users and a lot of users, and someone could, maliciously add users. And at that point, you kind of, every time you run this loop, and every time you do the check, every time you update it, you use gas, right? And if you have a lot of users here, you're not going to get to the end of arrays where you need to go to find the name before you run out of gas. In which case, you can't really update your information. So this sometimes happen in, DeFi or DEX, where you update positions or you liquidate positions, but you use arrays. So that way they don't get to you. So you don't get liquidated, even if you, hit the margin. So it could be a serious issue as well. So the solution here is use hash map, right? You can basically use hash map to reduce O of n algorithm into O of 1. So in order to basically calculate the hash and then modifying the data directly is one of the ways to not use huge arrays. So the same code could be updated like this, where you have a mapping of username to index, and then you use the hash map. So the function signature stays the same, right? Update user info by name, you get the username and the age. But this time, you're not iterating through the array, but you're directly accessing that user's table with the hash. Yeah, so I think this kind of ends our session to cover all the not all some of the smart contract security issues that happen in our real life. If you're curious about more other examples, feel free to search SWC registry, and it's going to have like 30, 40 different types of vulnerabilities that you can make in Solidity. So yeah, so we're going to end it here for now, and then we're going to take 10-minute break and then come back and do the rest of the examples.